Hi, everybody. Today we're going to continue on our critical thinking systems analysis, except now we're going to focus more on machine programming and AI, but we're going to do it sort of from a quasi completeness perspective, which I hope, will shed a lot more light on why we made certain decisions at Merle with respect to the machine learning technology that we built and why we didn't necessarily make the foundational elements based in neural networks. But before I dive in, I want to give a shout out to our friends over at Dream Clinic. I'm listening to them in the background. And what are we listening to? Witch Seeker, which came out 2 weeks ago and super awesome, at least for me. So, Dream Clinic, we love you guys. It's fantastic. And coming up shortly, we just finished the formation of a partnership with OmniStraight, and I'll be doing a little bit of a overview of some of the cool stuff that OmniStraight's doing, but that'll be next week or something. So as a refresher, what we talked about last time with one way to do a more systematic analysis of things rather than looking at something and just saying, oh yeah, I like that this house has 2 bedrooms or that this car is the color blue. There's a way to, before we start doing soundness checks, we can look at things from a completeness perspective. And what I was trying to essentially get across is that if you start with completeness, even if you don't get perfect completeness, you may end up with a deeper and more comprehensive analysis, which will let you find solutions that you might have overlooked otherwise. And one of the examples we used was this smallest number thing. Smallest number when squared is between 7 and 24. And we showed that it's very easy to kind of get stuck in the space over here where you're just looking at positive numbers, since that's maybe where our head goes immediately. And while you'll get maybe the right answer for the positive number space, which I believe is 3 squared is 9. And so it's between those two numbers. And that's actually what Google got. When you expand the space of things that you're looking at and you look at negative numbers as well as neutral numbers, I think maybe there's only one neutral number, which is 0, you realize that a more comprehensive analysis gives you an answer that's different, which is -4. And this is an example of how completeness can help us make more informed decisions. So I want to share now, I think, at least some part of how we got to where we got with making decisions about machine learning technology at Merle, and what was part of maybe our discovery of the first principles and why these first principles emerged. So if we quickly revisit and by the way, just in interest of completeness, this is, from my perspective, an example of completeness. It's a little bit of a hack, but in this slide, I was trying to define machine programming, and I'm talking about its automation of any aspect of software development. And then later in this talk, I'll talk specifically about code reasoning, code actions, and then everything else. And the reason why I argue that this is complete is that I'm not trying to say that machine programming is only related to code. There's actually a huge segment that is not related to code. But the two pieces that I'm most interested in are reasoning and actions related to code, at least for this talk. But then there's a whole other space of other things, and that's really the catch-all with the everything else. So the everything else is basically my acknowledgement of saying, yeah, this is not exhaustive, these two things. There's a whole bunch of other things. I'm aware of that, but I don't really want to talk about those right now. So just maybe an example of me doing this actually for a real talk that we just gave a few weeks ago. Okay, so yeah, I would like to take a look at this first principles view. And part of how this came about was by doing an attempt at completeness analysis for machine programming through the lens of software engineering. Now, I realize that if you have never done software engineering, it may be really hard to have a completeness analysis of software development if you don't know all the pieces. And likewise, you would also struggle or maybe getting the right answer for this question up above if you don't have a grasp on negative numbers as well as positive numbers. So that would be the starting point, is that there's a certain core level of knowledge that one must sort of obtain, I think, in order to do some of these completeness analyses, which is why I will often argue that in order to do really important machine programming work, one will often need to know more than just machine learning. You will also likely need to know at least a little bit about software engineering, programming languages, and systems. And again, the reason for this, one, for software engineering, you kind of have to know this at least peripherally to understand what is the MP system I'm building and how will it help software engineering? Because if it doesn't help software engineering, why are you doing it? I mean, if you're doing it just for exploration purposes, that's great. But if you're trying to build a system that has actual value to other people, then we should understand what actual people do when they're doing software engineering, which is what we're going to do here a little bit. Then understanding programming languages often is important, because if you don't understand just general PL design and the implications of certain design decisions, it may be challenging to solve an engineering problem that you're very interested in a way that's pragmatic for the embodiment that's used for that engineering. And what I mean is the embodiment is sort of the code, and the code is implemented in a specific language. That language is the vehicle we use to do software development, or many languages, right? And then systems is more like about performance oftentimes. It's sort of like, why is this slow? What can we do to make it faster? Is it that we just don't understand systems well enough and a better understanding of systems would make it better? Or is it that we do understand systems and that this is just potentially computationally intractable, right? So this is a lot to ask, I realize. And I don't think that anyone needs to grok all of these to do machine programming systems, but I do think you probably want to have at least a peripheral sense of those other three domains in order to build a machine programming system that will have value to others or even yourself outside of just being a toy. Okay, so here's the first principles. I'm just going to leave this up, and I want to quickly take a look at how one might sort of derive certain properties that may be integral for a machine programming system by looking at it through different lenses. So the first way that I want to look at is through the language model lens, which is how I think a lot of people are building machine programming systems today. I think the majority of the code assistants are doing this. And what I think they do is they begin with the soundness check of like, okay, a language model, well, we know that it works for NL, so that's a check. And then, oh, there's some data that shows that it works with programming languages, at least anecdotally, so that's a check. And so now that we have this, and oh, this is readily available from things like Hugging Face, I can download this, and we can then serve the results of inference to consumers on commodity hardware through like a cloud to consumer type of system. On top of that, we can fork things like visual code, and then we can integrate our AI directly into the IDE. And therefore, I think from this, you get these IDE plus language model solutions that is equal to whatever it can do. Now, notice that when you look at it from this lens, you sort of have already started with the answer. Like, you know what the answer is. The answer is language model. Why is that the answer? Because you chose that language model is the revolution, or it's the fancy new toy. And so clearly this is the thing that you should be using because everybody keeps talking about it. From this lens, you've already married yourself to constraints of the space of only things that can be solved by language models. One of the most dangerous things with neural networks that is a byproduct that a lot of people are stuck with because first principles is they're not considering sort of the things that we have here. Instead, they're saying the first principle is this axiom that is written in stone is it will be language model based. Why? Because it's fancy and everybody talks about it, and that's what we're going to do. Okay, so I personally think this is not a good way to build a company. It's not necessarily a good way to advance science. I don't think this is a good way to do research because you've already like preemptively decided what the answer is without even looking at what the constraints of that answer may be. And one of the constraints, actually, like two critical ones, is these are potentially non-performant unless you are having cloud support. And what about the cases where it needs to be like on-prem and stuff? Again, you sort of already married yourself to this, so you don't have much flexibility. And the other one, which is really a doozy, is the stochasticity of it. It's stochastic. And we're going to get into this quite a bit on how this is a deal breaker, at least from my lens. So this is what happens, I think, when you don't do a completeness analysis first, and you go back to like these 4 pillars, and you're basically saying, this is the hot area. I want to apply it to this. I don't actually really understand this deeply, but I understand this piece. And I know that I can just download some stuff. And then what if I just do sort of, I put all these pieces together, shake it up, and then see what happens. And I'm not trying to be like insincere. I mean, like, I know a lot of people that actually were thinking or doing just that. That's what they were saying. It's like, listen, I'm going to take all the stuff and it's going to have novelty through composition. The downside of that approach, I think, just in general, is all the things that are easy for you to do are also easy for everybody else to do. So they can also download this from Hugging Face. They can also set up a cloud instance, and they can also fork visual code. And so you get into this, everybody is fighting over this low-hanging fruit because it doesn't like require a lot of work. It's not super hard. And it's also, in this case, significantly suboptimal in terms of a reasonable solution for software engineering, which hopefully will become super apparent, just like the examples that we looked at last week. When we include the negative numbers, we realize, oh, 3 is not the answer, it's -4. But when you don't see those negative numbers, it's like very easy to get tricked into thinking that this is the right way. So instead of deciding what the architecture or the machine learning thing is going to be, another way to approach this is from this angle, this lens of completeness, from the actual application, the domain that you're going to utilize your machine programming system in, which in this case is software engineering. Or we'll just say software dev. Okay, so what does software development look like? Well, one of the easiest things to reason about is there is code writing. And by the way, what I'm doing right now, I often refer to this as like I'm doing the Archimedean spiral. And the reason why I call this the Archimedean spiral is, for those of you not aware, the Archimedean spiral is sort of like this thing. This also just happens to be the shape that they use, like in one of my favorite movies, which is Dark City. And if you haven't seen Dark City, just a side note, it's a little bit old, I guess. I mean, not for me. I still think of it super fondly, like it was just yesterday. But I guess it's been a while now. But if you don't mind it being like 20 years old or whatever, really awesome sci-fi movie. I won't say anything else. But Goju loves this. That's my attempt at a heart. Okay, so the Archimedean spiral, what I'm trying to do here is say, we're going to start at the starting point, which is the inside of this spiral, and then we're going to start to iterate around. And as we iterate around, we're going to get deeper and deeper and deeper. But we have to start somewhere, and oftentimes where we start, we don't know everything that there is to know. Like, we will tease out information as we do more and more revolutions, and each revolution we make, we go deeper. We start to understand things more, but we do a full sort of complete pass each time, so we don't go too far down any rabbit hole where we're looking at something that's potentially the entirely wrong answer. Which is why we stay away from things like deciding preemptively that a transformer-based solution is the answer. Okay, so now if we go back somehow, okay, let's see if I can figure this out. All right, so we have code writing as one part of the development process, right? So this is just overview of software development. We'll say these are phases or important aspects to software development. And for those who have not done a lot of software engineering, or they have not written production quality software, one might believe that this is the crux of the problem, is writing code. But as I think many of you have seen and said in the GTT poll, what do you think is the hardest part of software development? It's the iteration. And this is from all of you Jeters. This is not me saying this. It's overwhelmingly, it was like 60% people were saying it's not the writing the actual code, which is one piece. It's this other piece, which is, this is like code adaptation. This is the part that people are spending a lot of time in. Say a lot of time. Okay? And this is not a lot of time. All right. And then on top of that, in addition to just adapting the code, there are these other pieces that are like, they may be part of code adaptation, but they're more a little bit, I would say, about a deep reasoning and understanding before you start to adapt the code. And we'll call this like code reasoning. And these would be things like we are debugging, we're profiling, we are testing. Let's just say that it's all sort of in this. And now there's more phases, right? There's like the actual deployment that we do, pre-deployment, post-deployment, there's sandboxing, there's staging deployments. There's a bunch of things that, like creating sandboxes. There's a bunch of stuff, right, that's related to this. And this is a bit of a oversimplification, but let's just stop here for the time being. Mostly to just try to highlight a very, very important point, I think, in why we didn't use language models foundationally for our AI system. When we think about building a product, right? Because this is going to be the product that we're going to build. We're going to do, let's say we're going to have some time here, and this will be mostly to start. So when we're first creating a product, this is going to be a lot of the work. Maybe let's say that this is like 90% of the work initially for the first 6 months or something. Then after we get through maybe the first year, so let's try to draw sort of like a timetable here. So you've got like, this is year 1, and it's mostly, we'll call this CW for like code writing. So like code writing. And then let's say year 2, let's say you've got the product now kind of fleshed out, and now you're going to do some enhancements, you're going to do some profiling. So maybe you have a little bit more code writing, but then there's more of this code adaptation. So let's say maybe at this point it's like 50%. So this one we'll say, just to be overly generous, we'll say 100% of the first year is just code writing. There's like no adaptation. Then in this second year, let's say it's 50% code writing plus 50% code adaptation. And we won't even get into code reasoning and stuff. And then now let's say that like for year 3 to 5, it'll start to shift a lot, right? Because the product is maybe getting hardened. And so there's very little, let's say maybe there's like 5% of this code writing. And then maybe it's 80% of the code adaptation. And that gives us another 15% of the code reasoning, the debugging, the profiling, testing. And now moving on, let's say we go years 6 through N, which is, N is in this case, infinity. It's basically as long as your company can survive. And in this phase, we'll say it's like, okay, the code writing that's like new code is like 1%. The code adaptation, let's say, is like maybe 90%. So this is the code writing, this is code adaptation, and then this is code reasoning, which we'll say is like 10%. And this is what the timeline is going to look like moving forward. Okay. Now, this is the part where it's going to get maybe potentially a little wacky. We're looking at this list because we're trying to understand what software engineers do, and we're trying to build a product that will benefit them. And so when you think about these code assistants, they're principally, I would argue, the way that they're being pitched today is they're principally useful for code writing. A big reason for that is they struggle a lot with code reasoning because they have limitations in their context window, where if you don't have essentially $100 million to burn, you can only reason about a small amount of context, which basically means they'd be pretty good at taking a couple sentences of input and then outputting a small amount of code. But if you had them analyze a full repo, it's like, oh, this is not necessarily a good fit, right? Which is why you generally don't see language models doing repository level analysis in a way that's like meaningful. It may be that you point them to something and say, reason about this file. And again, if you say something like, hey, integrate or implement this feature, that's different than full repository reasoning in the sense that you're giving a guidance on how to do something, and then it may just start scanning individual things with this one thing in mind. It's not looking at the whole system saying, okay, let's look at all of the different dimensions of analysis for this system and try to figure out like how we can make it better. What's wrong from all these different dimensions. All right. Now, because of this limitation for code assistants, they principally are going to be used for code writing, which is cool, great, whatever. When we look at this timetable, we immediately notice, again, if we believe this, I suspect maybe a lot of the senior developers can chime in and talk about what their experience has been, or maybe I'll run another poll. But you can see as you move further along, it becomes less about code writing and it becomes more about code adaptation and code reasoning. And I could say myself from doing this in industry for 30 years, that's pretty representative of what it's like. First year, bang out a whole bunch of code, and then for the rest of your life, maintain it. Okay. So this raises maybe the first question. If most of software development is maintenance of code, are code assistants like that valuable if they're not really good at maintaining? They're only good at writing new code. Now, I want to be clear. I still think code assistants have value, at least in two dimensions. One, I think they're excellent for teaching software developers potentially new languages that they have not programmed in before, mostly just to help them understand syntax. And I use them like this to level me up for JavaScript, right? Because I'm a terrible JavaScript programmer. Or TypeScript or other things that like I don't remember the exact syntax, but I know semantically what I'm trying to achieve. And then the code assistant is like, oh yeah, write this. And then it like teaches me the syntax and then I write it myself. Very valuable, I think, from that lens. The second lens is I think they are also very useful for research prototyping or rapid prototyping or low fidelity prototyping where you have an idea and you're like, okay, I don't know if I can do this idea. Code assistant, can you try to build me this thing? I think super, super valuable for this. Now keep in mind, this prototype is not necessarily going to be performant. It's not necessarily going to be correct. It may not deal with the corner cases properly. So you should probably be very careful to not take the answer that you get as like, oh, this works, because what you're probably seeing is more just a straw man. What you're seeing is that it is giving you an illustration that the hypothesis you had has some embodiment, but the embodiment may not be complete. It may not be comprehensive. And that comprehensive portion, that part could actually be a deal breaker, that when you try to actually make it complete, it's like, oh no, the performance plummets, or oh wow, this doesn't actually work in this environment. I wanted it to run on the edge and it requires it to be on the server. There's various things, right? But anyway, all that stuff aside, I still think that code assistants have value in this space. But if we believe what we've just drawn here as representative of what software development really looks like, then we're in a bit of a pickle, right? But here's the rub. Is that as you're building machine programming systems, they are software development systems themselves. So when you use machine learning systems, the same breakdown is likely going to apply to you as the machine programming developer, as the folks that are using your systems for their development process. So what do I mean exactly? What I mean is that as you're building these systems, let's say it's a code assistant 101, we'll call it CA 101, and you're actually writing all the code to make this thing super awesome, right? It's going to be super amazing. And you start and you have version 1 and it's using your language models, and this thing is incredible. It's just like A+. Everybody loves it. Fantastic. Massive splash, you're making headlines, you're making revenue, or people love your work. And then you're going to be asked to maintain it. Let's upgrade this. Let's now roll out version 2. And of course, version 2 has to be better than version 1. Otherwise, why do you have a version 2? Well, you're using language models, and language models are stochastic, and they also lack things like understandability, interpretability, repeatability is up here before this. And then last, debuggability. Now, there are very smart people that are trying to make neural networks repeatable, understandable, interpretable, debuggable. But to the best of my knowledge, we haven't made too much forward progress. And I want to remind everybody that neural networks first emerged in the 1950s. It's been about 70 years that we've been building neural networks. And this is still a problem. It's not like neural networks were just invented last year. And so it's like, oh, this is new. We just need some time to figure this out. For 70 years, a lot of scientists, a lot of researchers, a lot of really, really smart people have been trying to make these systems repeatable, understandable, interpretable, debuggable, and they're having a heck of a time. So now let's just try to understand, for completeness sake, going back to the software development cycle, is that you have this space, right, of this code adaptation, because you're going to be like fixing bugs, and you're going to be like adding these new features. And when you add new features, you don't want the old features to break. You want it to be compositional. So the old features, they all still work, and you have more features now. And when you fix a bug, you only fix that one bug. You don't accidentally introduce other bugs or have other crazy side effects. Now, when you have a system that is stochastic, first of all, you lose repeatability. Without repeatability, it can be very hard to understand how this thing works, to interpret it, and to debug it. Now, if you can't debug the system, how can you reliably improve it for things like iterative refinement? How do you do iterative refinement? So some people might say, oh, well, that's easy, Goju. All you do is you get more data that you know is good, and then you add that more data, and then you retrain it with the new data and the old data, and you're golden. If only that worked. The problem is that you don't know what the outcome is going to be when you train on the new data with the old data. It could absolutely break all of these things. Some of you might be saying, oh, well, one of the ways to do this is you seed it. You seed the neural network with the same seed for the randomization elements when you build a new neural network. So you get the same pseudo-random numbers for the initialization of the weights and things like stochastic gradient descent. And then when you add the extra data, it'll get you the first model part exactly the same, and then you'll add in the second pieces. Sure. That first part is correct. You will likely get potentially the same model. But the question is, what if that model won't work with the new data? Well, then what you would do in the real world is you would say retrain it with a completely different seed, with different hyperparameters, with all these different things. Well, that means The thing that you had before in version 1 that everybody loved, you don't even have that. You're actually back now at, you're not version 2, you're version 0. And then you're trying to build version 2, but there's no guarantee that what you're building is going to be as good as version 1 was in all the spaces that it was, as well as doing the new things. It could be that version 2 is really good at the new things, but not so good at the old things. And now it's a question of like, well, what if the people only care about the old things, right? And I think that there's some complaints about this with GPT-5. I haven't had time to play with it myself, but I've heard a lot of people saying, oh, it's actually getting worse. Of course it is, right? Because it's a stochastic system. And then because it's stochastic, you lose the ability to do iterative refinement. In addition to that, because you don't understand it, and you can't go in and change things directly that have a direct impact on what the behavior is. You can't go in and say, change this weight, this will actually fix this specific thing. You lose the ability to perform iterative refinement in a way that fixes just a single aspect. Now, this is why when we were doing the completeness analysis for Merle, and we were thinking, how are we going to build the system? We made the decision right out of the gate that, okay, wait, so first of all, let's assume we succeed. Let's assume that we're going to build this thing and people are going to like it. Then what? Then version 2. Okay, so how do we do version 2 if we're building off of a stochastic system that we can't understand? You don't. You don't. And therefore, determinism is a first principle. You sort of need determinism. And I want to be clear here. You don't need determinism for the consumer that's using the thing, for the users, right? The determinism for ChatGPT or Claude Code or whatever, sure, maybe they like that. That's great. You need the determinism so your own system can evolve in a way that you can control. Because if you don't have that deterministic behavior, you can't reason about this in a reliable way to where you can say, okay, I changed something. Now it's deterministic. You fixed this thing. Did everything else stay the same? Okay, it did. We're good. Oh, it didn't. Oh, we didn't fix it right. Right. So minimally, you want this determinism not as a property of the system that you're deploying, but as a property inside of your own software development process. Which is why, from a completeness perspective, if you build production quality systems that principally rely on language models at the foundational level, it's going to be very hard with today's technology to perform iterative refinement. And all of the science that I've seen, all of the advances in technology that I've seen, the reason why we have the computers that we have, the phones that we have, even like the controllers that we have, like this is, I think, a really good one. This controller, this is maybe the 20th generation of this controller, and it is really different from the original. Imagine if you had version 1 and version 20, and version 20 was worse. So I wanted to share this now that we've gone through the completeness perspective, because this is actually what we did at Merle, is we looked at software engineering and said to ourselves, one, where do people actually spend the most time doing software development? Oh, it's in code adaptation. So maybe we should focus on that problem, since that's the key thing. And then we thought, okay, we're building the system. How do we build it so we can iteratively refine it, knowing that it's not going to be a roll the dice once. It's not a one-off. We're not building Mona Lisa here, where we draw it up and we're like, okay, it's perfect. We're done for forever. Instead, we know that we live in the world of iterative refinement, and that if we're successful, if we're lucky enough, you get to something like OS X, you get to something like Windows 11, you get to the nth version, because people are so keen on your products that they keep buying it and they keep getting better and better and better. You get like the iPhone 16. And really one of the key properties of that is the support of iterative refinement. Now, I'm not trying to say what anybody should do. I just thought that this would be kind of interesting to share from my perspective, given that we were talking about completeness and how when you do a completeness analysis of problems, as we saw last time, you often end up with like more correct answers because it's more comprehensive. You're like looking around saying, okay, well, here's all the things that we could do. And what are the things that we need to be successful here? And rather than coming up with the number 3, you look more than just positive numbers. You look at negative numbers and you realize, oh, it's -4. Likewise, in the same vein, when you're building a machine programming system, rather than just preemptively deciding, oh, well, of course it would be language model based. Of course it would be based on transformers because that's what everybody's using. There was a time where the whole world thought the Earth was flat. Flat earthers. Just because everybody's doing it doesn't mean they're right, especially when it's something new. I think we discussed before, there was a time where literally doctors were saying, like, here's the best cigarette that you can smoke. Like, doctors were saying you should smoke cigarettes. Today, I think that we don't do this. There's also a time where, like, we used to bleed people. Bleeding, you can look it up, right? So the point I'm trying to make is just because it's fashionable right now and everybody's doing it doesn't mean they actually know what they're doing. It could very well be that this is an emperor's clothing thing, and a lot of people haven't really thought through the ramifications of the decisions they're making. They just are like, well, everybody else is doing it. These things are cool. Let's just throw it together and do stuff. But if you actually sit back, take your time, do a completeness analysis, and realize that the majority of the time that you're going to spend in software development yourself is in the adaptation, and then you realize that you're using a machine learning technology that is not adaptable, not reliably adaptable, I mean, that sounds like a deal breaker to me. But hey, people are going to do what they're going to do. So thanks, everybody. That's the end of this episode. I think we're maybe good for critical thinking and system analysis. We'll talk about OmniStraight or other things next time.